All right, we're going to be looking at 1.6, last section in the first unit, complex number system. And so looking at imaginary numbers and all the things that go with it. So objectives, the imaginary unit I and its properties, the algebra of complex numbers, so some of our arithmetic that we use for complex numbers, and then looking at roots and complex number, looking at more radicals that involve pulling an I out and things like that. So let's jump in. What in the world is an imaginary unit I? I is the square root of -1. Good luck plugging that in a calculator. So this is, it's a very interesting thing is that it's not a real number. So we've talked earlier in Unit 1 about real numbers and all the numbers that are, that are subsets of the real numbers like rational and irrational and integers, whole and natural. But with something like I, we call that an imaginary unit. And so that falls outside of the reals. And so we call these more of the complex. And so the imaginary unit I is not real, it's not in the same family, but we can do a lot of higher level math and things that are applicable. And so I know a lot of times we think, well, it's like imaginary, it's made up. It's not. The name of it, I wish they wouldn't call it imaginary because it makes it things like it's made up. It still has certain rules. It has to follow mathematical rules, and it has to be true all the time for it to be a part of our math arsenal. And so the square root of -1, or this I, allows us to do a lot of things when we call complex numbers. When it comes to electrical work, anything with like vectors and things like that that are utilized quite a bit in physics and other areas are going to be using these ideas complex numbers. So what we're going to do is we're going to look at the imaginary number I. And so we usually just leave it I, but it is the square root of -1. So keep in mind, I is a radical, square root of -1. And then what we're going to do is we're going to be looking at square roots of negative numbers. And so, in other words, if we have the square root of -4, how do I handle the square root of a negative is what we want to do. And I'm going to show you the long way, is we want to go ahead and rewrite this sort of like this. And then what we use is, remember, we have properties of radicals, and we have one is that is the um, product property of radicals, which says I can split this up. And so we get something like this. And then we can evaluate these individually. Well, we just said the square root of -1 is I, and the square root of 4 is 2. And so what we end up getting is 2i. So there's the long way of doing it. What we're going to do is, if you have the square root of a negative, we're going to drag an I out. We're going to take our I out. Remember, if it's a cube root, fifth root, seventh root, odd indices, the cube root of a negative, the fifth root of a negative, simply means your answer is negative. So there is no I for those. But for square roots and fourth roots and things with even indices, now what we're going to do is drag our I out. So let's do another problem similar to that one, but instead of the longer way, let's do it this. We have the square root of a negative. If it's a square root of a negative, we want to drag our I out. That takes care of the negative. And then we can go ahead and evaluate the square root of 9, and we get this 3i. So when you see the square root or any even index of a negative, drag that I out. Take your I out. And if it's the cube root of a negative, that just means your answer is going to be negative. So a couple more examples. We just did the square root of -9, so we don't need to do that one again. Let's do the square root of -72. And so what we do first is always take your I out first. And this will come into play at the very end of this lesson. You'll see why. But for right now, might as well put it in there. Put it in your notes. Always take your I out first. So we have the square root of a negative, so we take our I out. And then we can go ahead and look at evaluating the square root of 72, like we did in earlier sections. So this breaks down to 9 and 8. So 9 breaks down to 2 3s, and 8 breaks down to 3 2s. And we're putting things in groups of 2, so I can take a 3 out and a 2 out, aka we can take a 6 out. So I'm going to take a 6i, and then we have the square root of 2. Now, that's how I sort of prefer writing it right there. Sometimes what you'll see is if they want it in specific complex form, the I will be last. And so occasionally you'll see an answer that's written like this, and then the I is still outside the radical, but it's sort of last. But I like throwing the I right in front. And so for me, that would be perfect kind of thing. But you can put the I at the end as well. Okay. Now, what I want to show you here is, okay, what if we wanted to evaluate something, an I that's maybe a larger I than just I? And so show you a document here that will help. And so what we have is that the powers of I sort of go into a loop. Okay, it's like a wheel. And so I sort of think of it a little bit like the Price is Right wheel, where at the end where they spin it, it really doesn't matter. And obviously it has to go around once, but it doesn't matter how many times it goes around. What matters is what it ends on. And so that's what we're going to end up doing when we have to evaluate, let's say I to raise to some power, is what we're trying to figure out is not how many times it goes around the circle here. What we're trying to figure out is where does it end up? Click, click, click kind of thing. And so that's what we're looking for. And so there's going to be a strategy to do that, but this is sort of neat. I'm going to post this on Google Classroom so you have access to this. But I do want to show you at the bottom, it sort of has some things there that you can sort of fill out and keep it going. So always divide the exponent by 4. The next slide's going to have this information on there. This is very much more organized. So let's go through it here, but the next slide's going to have it as well. So what we're going to do is we're going to take the exponent and we're going to divide by 4 because there's 4 different values that I can take on. So it's either I, which is I to the first. If it's I squared is simply going to be the square root of -1 squared. And so the square root of -1 squared ends up being just -1. So the remainder, so 2, I squared is -1. Let me bring this back up. So I is the square root of -1. I squared is -1. I cubed, which is amazing. I shouldn't just go past it like, oh, this is just anything. We just made an imaginary real, which is quite interesting and very useful as we do math. And then I cubed is simply I squared times I, right? So we have the square root of -1 times -1, so it's the opposite of I. And then I the fourth is simply I squared times I squared, so -1 times -1 is 1. Now I to the fifth is simply I to the fourth, 1 times I. So 1 times I is I. So I to the fifth is the same thing as I. And then we go 6, 7, 8, 9, and we keep going around the circle depending on what the exponent is. So there's only 4 possibilities that our answers can be. So to figure those out, what we want to do is divide by 4 and figure out what the remainder is. Okay, and the remainder is going to be your exponent. The only one that doesn't come out like where the remainder is your exponent is if there is no remainder of 0. If it divides evenly, then that falls into the same category as I to the fourth. And so the table at the bottom, I'll just verbalize these to you. I squared, which is -1. I cubed is the opposite of I the fourth is 1. Now, I the fifth, if we divide 5 by 4, we get 1 with a remainder of 1. And I only care about the remainder part. The 1 on top, the quotient of 1, just says how many times have we gone around. I don't care. I want to know what I land on when I spin the wheel. So I get I to the first, which is I. Okay, so we leave I the first as just I. I the sixth, we divide by 4, we get a remainder of 2. That's I squared then, and what is I squared? -1. So we definitely need to memorize these 4, and then how do we find them if they're other exponents? 7, remainder of 3. Okay, that's I cubed. What's I cubed? The opposite of I. 23 divided by 4. What you get is you get a remainder of 3. And so that's I cubed, which is the opposite of I again. 28, it goes into it evenly when we go divide by 4. So that's the same thing as I to the fourth. So if you get a remainder of 0, it's like having I to the 0 power, which is 1. So I to the 28th, the same as I to the fourth, which is 1. 34 divided by 4, we end up getting 8 with a remainder of 2. Remainder of 2 is I squared. I squared is -1, so we'd have -1 there. 121 divided by 4, you get like 30 with a remainder of 1. Again, all I care about is the remainder of 1. And so it's I to the first or I. And so wanted to show you that. That will be a file that you can utilize. And so let's go ahead and we're going to head back to our slides here. And so this is sort of now applying what we just talked about. And so the process for simplifying is simply with higher exponents, take the exponent, divide by 4, and the remainder will tell you that. But we do need to memorize these 4. So for remainder of 1, okay, we get I, and I is simply I. Okay, now if we get a remainder of 2, it's I squared, which is -1. I cubed, remainder of 3 is the opposite of I, and remainder of 4 is 1. Or excuse me, a remainder of 0. We won't get a remainder of 4, but I the fourth, which is 1. Other ways of looking at is whatever your remainder is going to be your exponent. So if you get a remainder of 1, it's I to the first, which is I. That makes sense. I squared, which is I squared, is -1. I cubed. And even it works down here. If you get a remainder of 0, put the 0 there. Anything to 0 power is 1. So it works out. Whatever your remainder is, make it your exponent. Then you just got to memorize those 4. or at least understand where those 4 come from. So I to the 47th, we take 47, we divide by 4. And what we end up getting in this case is 11 times around, and that's great, but I don't care about that. What I care about is the remainder. So it's 3. So I take the remainder, I make it my exponent, and then I memorize I cubed is the opposite of I. So I to the 47th is the same thing as the opposite of I. Looking at the bottom one here, we have negative I to the 8th power. So you can do this a couple different ways. You can either share the 8th power over, and then simplify that first half of this and then figure out the square root of negative 324 and go from there. So that's perfectly fine. You can simplify the radical and then combine them, like get it to where it's an I. So let's go ahead. I'm just gonna go ahead and deal with this for right now. And so what I have is the opposite of I to the 8th. So I'm going to share this to the negative. Well, negative raised to any even power is a positive. So I get I to the 8th. And I to the 8th is the same thing as I to the 0, which is 1, or I to the 4th, I should say. But our remainder is 0. And so you can look at it as anything to the 0 power, which is 1. So to be honest with you, this right here is gone. Okay. So that's pretty cool. So really all I'm looking at is the square root of negative 324. So what's the first thing we always do? The square root of a negative, take your I out. Cube root of a negative means your answer is negative. Square root of a negative, take your I out. And then what we do is we can break down 324 and see what goes into it. So I believe a 4 goes into it, and it goes into it 81 times. And then what we have here is 2 and 2 and 9 and 9. And so this actually works out really nice. I can take a 9 out and 2, that's an 18. So we get 18I. And that's what we have left. And that would be our answer for that one. Okay. Moving along, complex numbers. I had mentioned them earlier that imaginaries fall inside this complex, but really all numbers do. So we're expanding the family of numbers here. Real encompassed everything before you knew complex. Now, reals are now inside of complex. Reals are complex and imaginaries are complex. So we've added to the family tree a little bit. And so a complex number should be able to be written as A plus BI. Every number you can think of at this point in your math academic career should be able to be written as A plus BI, where A is what we call the real of the complex, and BI is going to be your imaginary component. So if I had a purely real number, then all we have is, like, let's say 4. It's like, oh, how do I write the number 4 in that form? Well, wouldn't it be 4 plus 0I? Okay, so it's in complex form, but 0I is just gone, so it's just 4. We can write a purely imaginary number by making a 0, and then we would have whatever BI is. So some of the problems you may have is they give you a complex, and they need you to identify either the real and the complex or what's your A and your B. So down at the bottom, you can see an example. The number 2 minus 3I is a complex number. 2 is your A, negative 3 is your B. If I said, what's the real part? It's 2. And what's the imaginary part? Negative 3I. And so that's our complex, is A plus BI. And this is a little bit piggybacking what I just said, with A being the real part, B being the imaginary part. And so we talk about purely imaginary or just a real number like 4, like I have there as an example. So pause and look at this if you need it, or write it down for notes, but I'm moving to the next slide. Okay, so here's what I was talking about. Complex numbers encompasses all the reals that we did earlier, but also inside of the complex, now what we have is these purely imaginaries. And so we're just expanding out our family tree of numbers into these complex. So we want to get to the algebra of the complex numbers. And the beauty of the algebra of complex is for addition, subtraction, even multiplication to a certain level. But addition and subtraction is going to be exactly like what we did with polynomials. So we're going to be adding and subtracting like terms. So don't overthink these. The real stuff's going to go with the real stuff. The imaginary is going to go with the imaginary. And then we just simply add and subtract like I is a variable. Now, I is not a variable, but we're going to sort of treat it like it is. And so what we're going to do is simply treat complex numbers like they're binomials, like it was 3 plus 4x or something like that, because you're very comfortable with that. So we might as well just do something that you're already familiar with or talk about it that way. So how we do this through addition, subtraction, and even multiplication is we're going to go ahead and combine the real parts and combine the imaginary parts. Multiplication, we're going to multiply. Now the difference though is if we get something like x squared, we leave it x squared with polynomials. With complex, if we get I squared, we need to convert that over to -1. So when we get to multiplication and some of the examples, you'll see that, but make sure our answers, every answer we get, should be able to be written in this form. So we shouldn't have I squares or I cubes or I to the fourth, nothing like that. Those should all be converted over to where every answer you get should be able to be written in complex form, A plus BI. And so that's what I have at number 2 is make sure to put the value in complex form, A plus BI. So if we look at these, look at this as simply a binomial plus a binomial, combine like terms. 6 plus a -3, which is 3. Then what we do is we do 2i plus 5i. 2i plus 5i is 7i. And would you agree that's in complex form, A plus BI? So we know what our A is and our B, and we're done. That's it. Okay. Once, just like polynomials, though, we got to be careful and distribute the negative through a quantity like this. So if you wanted to rewrite this, or do it in your head as you look at it, if you feel comfortable with it. But we go ahead and distribute, and so that's going to be a +2 and a -4i. And so what you'll see here is my 4i's are going to cancel, and I have -1 plus 2, which is 1. So really just the combination of those is +1. Okay, so just treat them like they're variables. Same with multiplication, but we have to clean it up at the end. So a problem like this, these are not conjugates, so we've got to FOIL it. But look what we got coming next. Okay, but let's go ahead and do the FOIL here. So we've got first, which is 8, outer, which is 2i. Then we've got inner, which is -12i. And then we've got last, which is -3i squared. Okay, so I'm going to go ahead and combine these two, and I get 8 minus 10i. So just like it's a variable. So I got my square there. The difference, though, is when these were variables, this would be our final answer. We wouldn't be able to do anything else, but we do know what in the world I squared is. So this is not in complex form. We've got to go ahead and convert this. So this is -3, and I squared is -1. So this is technically -3 times -1, which is 3. And so now what we have is a +3 over here. We can combine those and look at your answer. Now it's in complex form, A plus BI, or A is 11 or B is -10. Okay. I mentioned over here, these two are conjugates. So as long as you recognize they're conjugates, then you can save yourself a little bit of time by, instead of foiling, you can just it. And so that's good to know. We can do the same thing as just first and last if they're conjugates. So you get 81 minus 25i squared. I squared is -1. So what we get here is we get -25 times -1. And so that's a +25. And we add those two up and we get 106. And that's quite interesting. And then why it's interesting is we started with a complex and I used a conjugate and we got real, and that's going to happen every time. So that's interesting because when we get to the division and we have, let's say, an I in the denominator, that means we have a radical in the denominator because I is the square root of -1. So in order to get rid of a radical in this case, what we can do is use the conjugate like what we did with radicals, just basic radicals, and that should convert it to real for us, which is a non-radical because it's an integer. Okay, so that's what we're going to talk about next is the division of complex numbers. In order to rewrite a quotient in standard form, we want to use the complex conjugate. And so we know what conjugates are. Just make sure to do it to the top and bottom. When you write your solution, make sure you put it in the correct form. So be very careful with this. I'm going to show you what I mean by that. And with on Hawks, they're definitely going to be picky on how you're going to do this. And so want to make sure we write this properly. So if we look at an example such as this, what we have is 26 over 1 plus 5i. The issue is that if we have I in the denominator, what we technically have is a radical in the denominator because I is the square root of -1. So we're going to end up needing to rationalize, and we're going to use the complex conjugate, which is 1 minus 5i. And whatever you do at the bottom, make sure to do the top. And so we get something like this. Now, again, I'm going to hold off, just like we did with the radicals. I'm going to hold off distributing the 26. I'm not going to do that just yet. Okay, because I got to see what the bottom turns out to be. Because remember, we had some problems where the factor in the numerator and the factor in the denominator were the same, and we can cancel it vertically. So let's see what we happen. Again, these are conjugates, so I can flood this. So I get 1, and then I get minus 25i squared. Okay, so here's where the rationalization comes in, because I squared is negative 1. So I get negative 25 times negative 1, which is actually a positive 25. So I actually have 1 plus 25, which is 26. And looky there, luck be a lady tonight. The 26 is exactly what I was wanting. Those cancel, and we're left with 1 minus 5i, which is our correct answer. Let's take a look at the second one. This one gets a little bit more complicated, and hopefully on this one, things don't cancel as nicely, and maybe we can look at how to write these properly. So I dive in just like I did the other one. We're going to use the complex conjugate to rationalize the denominator. And so whatever you do bottom, do the top. I have conjugates on the bottom, but not on the top. So you got to FOIL the top. You don't have much of a choice. So 14 plus 2i minus 7i minus I squared. And so I will end up simplifying that in just a moment. And then on the bottom now, the bottom are conjugates, so you can flood this. So 49 minus I squared. So now what we need to do is just clean this up a little bit. And so I squared is negative 1. So look what we have here. We have the opposite of negative 1, which is actually a plus 1. And then the middle we can combine. So I end up having 14 plus 1 is 15. And then 2 minus 7 is negative 5i. So there's my numerator. Okay, my denominator, again, what we look at is very similar. That right there is going to be a plus 1, so we have a 50. Now, I'm not quite there. Hopefully what you notice is each term has a factor of 5. So let's go ahead and reduce everything by a factor of 5. So divide everything by 5, and we get here. Now, this is exactly what I want you to see. That is a really good answer. However, it's not in complex form. So in other words, it's not written as a plus bi. So that's not going to be exactly, if they say put it in complex form, that answer right there would not be exactly what they're looking for or what I would be looking for. But it's a really easy fix. If I want to make this in complex form, all you've got to do is you have a single term denominator of 10. So take that single term denominator and stack it underneath each term in the numerator. Now, on the right one, what we have is a 1 in front of the I. I know you don't see it, but it's there. There's the 1. So put the 10 under the 1 and then put the I out to the side, which means it's in the numerator, so we haven't changed anything. But hopefully now you can identify the standard complex form. Our A is 3/10, our B is negative 1/10. And so that's what we're going to be looking if they need it in complex form. Okay, a few more examples really quickly. We have this one. We have a negative exponent. Never take an exponent across a plus or minus sign. So I hope you guys, you owe me soft snickerdoodles if you do. In this case, let's go ahead and flip. There we go. And if I flip that, my exponent becomes positive 1, so I don't need it. And my issue is I have a radical in the denominator. And so we need to rationalize using the complex conjugate. So very similar to what we just did. So we get here. And the numerator just is 2 plus I. Let's see what we get in the denominator. We get 4. And remember, this is conjugate, so I can just flood. So minus I squared, which means 4 plus 1, because we get minus a negative 1 here. So we get 5 on the bottom. And then hopefully what you recognize is that's not quite in standard form, complex form. So what we need to do is take that single term denominator of 5, stack underneath the 2, stack underneath the 1, put that I out to the side, even though it's in the numerator, it's the same thing, and there's your complex form for that problem there. When it's a single term, we don't have a conjugate. These actually become a little easier. So you might throw in your notes this idea right here. When it's a single term, all you got to do is just multiply by I. That's it. Because if it's I and you multiply by I, it's I squared. That's real. If it's I cubed and you multiply by I, it's I to the 4. So and if it's even to begin with, like I to the 4th, then you just convert it immediately. But in this case, all you got to do is multiply by I, and it should make it real. And so we get I over I squared. And then I squared is negative 1. And so I wouldn't probably leave my answer like this. That looks a little weird. So we bring that negative up. And so the opposite of I is our final solution for that. Okay. Last thing we'll look at is operations involving sort of square roots. that have negatives inside of it. And really, there's nothing too tricky here. The biggest thing is this: before you use properties of radicals, before you start doing multiplication or breaking things down, you must always take that I out first. So rather than, I can't just start off by multiplying these two together. Okay, it will not work out because you're treating imaginary radicals, so radicals with negatives inside of them, like they're real. So the first thing we've got to do is we've got to remove the I from both of these. So we get I, then we get the square root of 24. Now that we'll be able to work with. Then what we have is times I, square root of 3, and so that we can work with. So we go ahead, and I'm going to simplify the square root of 24, which goes to 4 and 6, so I can take a 2 out because of the 4, and I left a 6 behind. Now, we could leave it like this, 24 times 3. I just did it so I don't have to multiply a large number, but you could go ahead and jump in and go from there. So let's go ahead and evaluate this. So I'm going to multiply the coefficients. So 2I times I is 2I squared. Square root of 6 times square root of 3 is the square root of 18, so we'll want to simplify that down, and that means we can take a 3 out and left a 2 behind. So if I take that 3 out, that means now I have a 6, 3 times 2. What's I squared, though? -1. So we get there, and then we have this 2 left behind. So -6 square roots of 2. If you would have multiplied those two to begin with, you would have got the square root of 72. And when you break that down, what you would have is 6 square roots of 2. And if it's 6 square roots of 2, it's obviously the opposite of what we got. So it's the incorrect answer. That's why you have to take the i's out first. So down here, do the same thing. Now you could do a few different things here because we can stack those two and simplify, and that's perfectly fine. I'm going to go ahead and get in the habit of just bringing the I out to begin with. So even though there may be a few other ways of doing this one, let's go ahead and take an I out of the top and an I out of the bottom. So the I out of the bottom makes I squared. Now technically I squared, we know what that is. It's -1. And so what we have is technically -2 now. 2 times -1, square roots of 2. On the top, we have that square root of 32. And I'm not going to rationalize. What I recognize here is the quotient property of radicals. So I could look at the square root of 32 over the square root of 2 as the square root of 32 over 2, which is the square root of 16, which is 4. So what I have in a box here is simply just 4. So I have 4, and then I have I, and I have -2, and that becomes -2I. So all that goes down to just a real nice -2I. So the key on these is really, we do a lot of radical work, but the key to get to being able to do radical work is take that I out first. So if you have a square root of a negative, make sure to take the I out before you do any kind of operations of real numbers.